Excellent. Okay. Good morning, everyone. Welcome to lecture 12 of Superconductivity, which is lecture 2 of the second block. As I was saying to some people here earlier, I don't normally bring coffee to these lectures, but as some of you will know, yesterday was the PKS summer party. In the immortal words of Dean Martin, did you ever feel so bad you'd have to rally to die? So we'll see what we can. If profuse sweating is the worst we get, we've got away with it quite lightly. So we've had a couple of lectures, one before the break and one after the break, about the BCS theory of superconductivity, the BCS ground state. I'm going to be writing that ground state a lot as we go on, because it's our sort of key to understand everything that's going on. So let me start with that. Product over k-states, some amplitude for not having a Cooper pair there, some amplitude for having a Cooper pair there. And I'm going to start being relaxed about hats on the operators. You know these C's are creation operators by now. So what I'd like to start talking about today is states that look like the original BCS ground state, but are different in some way. And this will get us into a discussion of order parameter symmetries. You will all have heard phrases like S-wave, P-wave, D-wave. This lecture is based on the assumption that you don't perfectly understand what they mean. And so we're going to go carefully through what these states are. I debated a little bit about which order to do this stuff in, because of course, if we're going to start writing down other states which are not the ground state of the BCS Hamiltonian, you might ask why we're writing them down at all. So we could have started with, alternative pairing mechanisms and where these states might come from, why a system might prefer to go into one of these variant states than into a fully gapped S-wave state. But actually, I thought it's easier to introduce the states first, describe their properties, and then we'll talk about why they happen and why some materials opt for these states rather than the conventional fully gapped S-wave superconducting ground state. But feel free to chip in with questions at any time. I don't mind mixing those themes up. So what did we have for these U's and V's? So U, I'm not sure, we actually wrote this in the notes when we did the BCS solution, but it follows, so remember we minimized the energy with respect to variations of these UKs and VKs. We got an equation out of that that gave us the gap. Also contained in that solution are the actual values that UK and VK take at every K. So I'm just going to write those down, and if I haven't written them down before, well, I'm writing them down now. They just come from the sort of mechanical optimization that we did a couple of lectures ago. And this ubiquitous BCS root is there. I've chosen a phase convention where the UKs are all real. That's obviously conventional because I could multiply the entire wave function by a complex phase and not change anything. So I've just used my freedom to choose the UKs to be real. In that case, the VKs are not real. Well, they might not be real. But actually for the state that we wrote down, yes, so I'll put an e to the I phi in front of it. And then we kind of, the same thing as on the line above, but with an attribution to the sides. Square roots everywhere, but that's BCS theory for you. So that phi is the relative phase between V and U, and therefore it is the phase of the superconducting order parameter. Right? So delta, if I define it locally at a given K, I might define as UK VK star. And so you can see that aside from all this kind of real gunk that I would have to multiply together, the phase of this is just determined by the phase of V. And remember, this phase is not a gauge invariant object. So by writing a particular phase there, we are picking a gauge. But there's some stuff you could only write down by picking a gauge, and these V's are one of those things. Just as a sense check, let's look at what happens very far from the Fermi surface. So if I go very far above the Fermi level, then this EK minus mu becomes large and positive, delta becomes unimportant, this factor goes to 1, so this becomes a half of 2, which is 1, so the U's go to 1 very far above the Fermi level. That's telling me that the states there are completely empty. And because of this minus sign, the V's go to 0, very far above the Fermi level. If I go very far below the Fermi level, then this is negative, and now it's the U's that go to 0, and it's the V's that go to 1. So this has all the properties that we drew in the diagram. This is just the mathematical expression for it. And Andy, it illustrates the point that I mentioned yesterday, which is that there's no momentum scale associated with crossing back over to regular excitations. Things just go like a planning. And in the theory that we've developed so far, this delta is the same irrespective of which K point we're talking about. So in original BCS theory, mod delta is independent of K. And that sort of makes sense. Our Fermi surface is completely isotropic. Our pairing interaction is completely isotropic. Why would it choose to make a superconducting state where delta varied with K? But we can consider generalizations of this state, which we create by introducing a K dependence of the delta that appears in these UK and VK expressions. Let me just say a word about why we would do that. And then I'll talk about what happens. So why might we do this? There are at least 3 reasons why you might think that there should be at least some anisotropy in the superconducting order parameter. The first is that in any real material, we probably have an anisotropic Fermi surface. There are a few materials where the Fermi surface is very close to being cylindrical or spherical, but it's never exactly that, right? There's always a crystal lattice. There are always some effects of that crystal lattice that sort of round off, create corners in certain directions and so on. And so just from symmetry grounds, if we have an anisotropic Fermi surface, there's no particular reason to expect delta to be perfectly isotropic, and generally it won't. There's another possibility. Both of these in reality tend to happen together, which is that we might have an anisotropic pairing interaction. So we've discussed so far pairing by the exchange of virtual phonons. And we looked at that, well, we sort of cartooned that as an attraction which is constant within a certain window of the Fermi level and 0 outside, and that's isotropic. But again, if your pairing is caused by something which comes from the lattice, then it's entirely possible that that thing, if you go to strong coupling, for example, you start sampling phonons that are not near the bottom of the band, they won't be perfectly isotropic. The phonon dispersion relation becomes anisotropic, obviously, as you get towards the end of the zone. Or you might have pairing which is due to exchange of other types of virtual boson, magnetic fluctuations, for example, if you're in the vicinity of a quantum critical point. All of this stuff ultimately comes from the lattice. The magnetic fluctuations come from the Fermi surface, so if the Fermi surface is anisotropic, they will be as well, and they will induce anisotropic pairing. So it may be that the actual bare strength of the pairing that you have in the Hamiltonian is different in some points on the Fermi surface than it is on others, and that would also be expected to give you an anisotropic delta. And there's another interesting possibility, which is you might have a non-retarded pairing interaction. Remember when we first discussed exchange of virtual phonons, we pointed out that, you know, it doesn't seem obvious that exchange of weak the weak attraction coming from virtual phonon exchange should be able to overcome the strong Coulomb repulsion between the electrons. And the reason it does is actually because of time delay. Right? It's that the attraction from the phonons is weak, but it hangs around for longer. That retardation of the interaction allows you to form Cooper pairs where the electrons are right on top of each other, because although they're right on top of each other, they're not there at the same time. This is all kind of swept under the rug when we write the BCS Hamiltonian, which is time local, but actually the effective attraction is retarded. Conversely, then, if you had a pairing interaction that wasn't retarded in time, then it has to compete with the Coulomb repulsion when you put the electrons on the same site, and it tends to lose. What we shall see is that some of these anisotropic pairing states don't involve putting the electrons on the same site as each other. Right? In the same way that only the S wave function in the hydrogen atom actually puts the electron on top of the nucleus, only the S wave pairing, Cooper pair wave function, actually puts one electron on top of the other. So I think one reason why we tend to see these non-S wave pairing channels in materials that are not phonon driven is because the interaction is not retarded, and so then it has to do something that doesn't involve putting the electrons right on top of each other.
Even anisotropic, we still consider the Fermi surface to be smooth, right?
Absolutely. So actually, for the discussion that we're going to have today, I'm still going to consider the Fermi surface to be circular. So we'll have the entire discussion just by writing these states down without asking whether they're actually energetically favorable. But as we come closer and closer to reality, we'll start to introduce these anisotropies, these sort of non-retarded pairings, and we'll show that under some circumstances these states are actually the optimum superconducting state.
So just to make contact with a very hastily prepared lecture I gave about unconventional superconductivity here last year, I knew that there was something wrong at the time, but I didn't really think about the anisotropic pairing interaction. I gave the non-retardation as essentially the dominant producer of non-S wave pairing state. Right, and that wasn't completely correct, and we kind of, Roderick asked good questions at the time, and I admitted it, but so what you're saying here, to my knowledge, is completely correct.
Excellent. Yeah, I mean, that surely you could produce models in which other things are at play, but I think it's some combination of these three in most cases.
And the non-retardation is the most interesting, I think.
I agree with that,
Yeah.
but actually, you know, once you break rotational symmetry, you expect anisotropy full stop.
Yeah.
Not necessarily nodes.
That's right.
Right? So nodes are another
The
thing.
non-retardation is what gives you, and not just nodes, it gives you a phase structure that gives you an autoparameter that cancels to zero under randomization.
Exactly. So we will talk about that as we develop this thing.
I guess there's a fourth, which is you could imagine there's some other broken symmetry that changes your Fermi surface to the point where, you know, you can't write down an S-wave pairing intrinsically, right? If you say, and that's not, none of these fit that list, it's neither anisotropic nor the pairing interaction being anisotropic. I mean, implicitly would be an non-retarded pairing interaction would be needed, but the kind of call, that's like sort of chicken or egg. Right?
Yeah,
So
okay,
break
that's,
symmetry,
yeah.
you change the Fermi surface.
Fair enough. So why don't we add that in? I'll take full credit. So transition above TC to a Fermi surface not compatible with that wave.
And I think you should put a little copyright sign and SID.
Great when your friends ask for the citations for you.
Log rolling, I believe is the phrase. Good. So we'll go later into models of this sort of stuff. There's a nice paper by Kazumi Maki from quite early in the Q-break days, actually, which has a totally physically unrealistic toy model that has a D-wave superconductor as the ground state. So we might go through that in a bit more detail, but let's just start with terminology and develop our pictures. So, if we have a weak coupling superconductor, then delta is very small, as we've already calculated. So the change of delta any change of delta in the direction perpendicular to the Fermi surface is probably ignorable, right? Even if the pairing is changing as you move in that radial direction, you lose the superconductivity so quickly as you move away from the Fermi surface that it's not really worth thinking about. So people tend to have this discussion in terms of how delta changes as you go round the Fermi surface. And so in the isotropic case, I can conduct this discussion by writing my momentum vector as a magnitude and a direction. And the hat on this does not mean that it's an operator, it means that it's a unit vector. And then what we want to consider is states where we just use the standard BCS form, but we say that delta now depends on K. There's some overall delta naught, which has, for example, the phase of the superconducting state in it, but it's multiplied by some function of this angle. And so that angle tells us where we are on the Fermi surface, and so this will give us an order parameter which varies as we go around the Fermi surface. You can think about cases where this is not a good language to use, right? If you have a Fermi surface that looks like this, then there are two different bits at the same angle, right? So you can have Fermi surfaces where this parameterization fails, and then you have to think more carefully about how you're going to uniquely describe where you are on the Fermi surface. But I'm going to assume for now that our Fermi surface is circular. This argument will generalize to cases where it deviates from circular but doesn't sort of fold back on itself. But if it folds back on itself, you have to think harder. Okay. So this is a function of angle and is telling us what the gap is doing. And like any function of angle, it can be decomposed into the relevant set of angular harmonic functions. And that set depends on dimensionality. So we're going to start off with the simplest non-trivial case, which is a 2D material or a quasi-2D material where the Fermi surface is circular. But then I'm also going to say something about cases where the Fermi surface is spherical and the material is 3D. So let's start with there's 2. Of course, in most real material applications, including the cuprates, we don't really mean that the material is two-dimensional. We mean that the material consists of sheets that are very weakly coupled to each other. And so the Fermi surface is, although 3D, approximately cylindrical. But that means the only angle that matters is the azimuthal angle in the plane. And so this is quite easy then, because we can just say that this unit vector is parameterized this way by that azimuthal angle. And any function of that unit vector can be written at more than one basis you could use. So I might sum over all of the complex exponentials that are consistent with periodicity. So that's just a Fourier decomposition of this function around the Fermi surface. M equals 0 is the bit that doesn't depend on phi. M equals 1 is the bit that oscillates once as you go round. M equals 2 oscillates twice. But quite commonly, people choose to use real harmonics, which is just an equivalent representation. So then you sum from M equals 0 to infinity these cosine harmonics. So M equals 0 is the constant one. And you then add again sum from M equals 1 to infinity of these sine harmonics. Obviously, there's no M equals 0 term in that sum because that's identically 0. So we can expand in the 2D case our angular dependence of the superconducting order parameter as a sum of different harmonics which are labeled by this angular momentum n. Yes.
In BCS theory, the delta is always along the Fermi surface, there's no perpendicular component.
In the BC, yeah, because the behavior as you change the magnitude of K is given in the forms of UK and VK. So, I mean, I could make that delta also depend on the modulus of K, if that dependence is sufficiently regular. But in weak coupling superconductivity, these things are going to, well, they're going to 0 or 1 very quickly as you move away from the Fermi level. And we only really care about what delta is doing in the range where both U and V are non-zero.
Because of the fact that the pairing is not in the window of a device frequency.
It's actually because the superconducting order parameter that we got from the BCS gap equation is small. So it is true that the pairing is only in a window of the Debye frequency, and so we don't care about stuff beyond that. Let me just give this as an aside. But actually, what we calculated from the gap equation was that delta goes like the Debye energy times this exponentially small factor. So actually, this is much less even than the pairing interaction window. And beyond this distance from the Fermi level, if you go up, the U's all become 1 and the V's become 0. If you go down, the V's become 1 and the U's become 0. And so then we don't have an order parameter because that's given by the product of U and V. So because of that, I'm just ignoring any potential weak dependence of this on the modulus of K and focusing on what it does as we go round the Fermi surface. A note for anyone who actually tries to do this in a practical calculation. If I have to think about the lattice and the fact that my K space is actually a Brillouin zone, I can't get away with this, right? Because this angle is defined with respect to the center of one of the zones. And it's, if I chose a different zone, it would be a completely different number. So I have to use a properly periodic function in K if I'm really writing this for a lattice theory. But for this purpose, I'm not really including the lattice. I'm assuming K space goes on forever, Fermi surface is circular, and then it's fine just to write it in terms of the angle. Good. Any other questions at this point? Yeah, please.
So is it okay if you have a multi-band circuit?
No, I mean, so multi-bands may give you multiple sheets of the Fermi surface, and then, I mean, then how to classify these things becomes complicated. So you'll have heard people say that the iron-based superconductors are S plus minus, for example. S plus minus is not going to appear in the classification I'm going to give here. This classification is strictly for a single sheet of a Fermi surface, which is centered at the gamma point. Anything else, you have to rethink. And actually, well, as we'll discuss, I mean, in any real lattice example, this classification is not really right. So this really does just apply to the case of an isotropic single sheet Fermi surface centered at the gamma point. People often use these phrases, S wave, D wave, and so on, for cases that don't correspond to that, but those uses are always somewhat incorrect and they can be misleading. We'll talk about that more as we get into the practical material examples. Other questions at this stage? Okay, so we can expand in these harmonics. One thing that's important to point out is that there is no reason at all to imagine that the optimum superconducting state will only contain one of these. So in the perfectly isotropic case, there's a reason for thinking that, because in the perfectly isotropic case, the only isotropic option is the m equals 0 cosine version, which is just the S-wave pairing. But as soon as you break the rotational symmetry, you can have all sorts of higher harmonics, and you may have many non-zero terms in this sum. And that's also an important point. People refer to superconductors like the cuprates as D-wave. They do not have the pure m equals 2 shape of the gap. If you actually measure what the order parameter is doing around the Fermi surface, and we'll discuss later how you do that, you find that higher harmonics are also mixed in. So it's correct to say that the cuprates are dominantly D-wave. They have the nodes, they have the zeros of delta in the place where D-wave would have them, but actually they don't just behave like a cosine in between those zeros. So this idea of classifying by harmonic actually only works perfectly near the critical temperature. In fact, it only works perfectly at the critical temperature. So it is generically the case that as you cool your sample, one of these harmonics will set in first. That's the superconducting transition. So right at TC, you will usually have a pure single harmonic form of the order parameter. But as you cool below TC, higher harmonics tend to mix in. You see exactly the same with other forms of order, right? Density waves and things like that. Just as a density wave forms, it forms by the conventional mechanism, at least, it's a perfect cosine oscillation of the density. But as you get deeper into the ordered phase, lattice effects tend to kind of square it off. And that squaring off is represented by the mixing in of higher harmonics. So just to mention that, we will be analyzing the superconducting states where we take just one of these harmonics, but that's, for a real material, that's a cartoon. Okay. So let's pick a particular harmonic. Which I have to specify by picking a value of m, and unless m is 0, I have to tell you whether it's the sine or the cosine harmonic that we're going to look at. And there is a way of drawing these things which people commonly use, which I'd like to show and discuss a little bit, because these pictures are often drawn and actually quite rarely explained. So what we do is to draw the Fermi surface. So this ring here is our assumed isotropic 2D Fermi surface. And then we draw another line where the distance from this line to the Fermi surface is proportional to the modulus of the harmonic that we're looking at. So this is m equals 0, and you can tell that because mod f is not changing as we go around the Fermi surface. And so if we introduce a coordinate system, there's this angle phi that shows us where we are on the Fermi surface. And at that point, this distance is proportional to mod f at that phi. We don't need to do it in this case, but we could. We write a plus inside this ring, and that tells us the sign of f. The absolute sign isn't so important, but what that plus tells us is that F is positive everywhere round this ring. So by analogy with atomic physics, M equals 0, right? 0 angular momentum is referred to as S-wave pairing. I don't know how many of you know what these letters actually stand for. SPDF stand for sharp, principal, diffuse, and fundamental, because of some historical reasons about what they looked like in early atomic physics diffraction experiments. So before they knew what they were, they just gave names to the scattering patterns based on how they appeared. And then, obviously, by the time they got beyond F, people had figured out what was going on, so then they just continued alphabetically. Yeah, so this isn't a perfect analogy, right? So it's not the azimuthal quantum number that gives us this letter in atomic physics. It's the polar quantum number, L, right? But nonetheless, people do it. So be aware that this terminology exists. Okay, we will go on to draw a few further examples. And I think I'll only clean one of the boards because it'd be nice to keep the S-wave on there as a comparison. What should we have? Okay, here's a challenge for those who know their poetry. Who wrote this? The trees are coming into leaf, like something almost being said. The new-formed buds relax and spread. Their greenness is a kind of grief. Is it that they are born again while we grow old? No, they die too. Their yearly trick of looking new is written down in rings of grain. Yet still the unresting castle's fresh, in full-grown thickness every May. Last year is dead, they seem to say. Begin afresh, afresh, afresh. Any guesses?
Wordsworth.
No, but that's a good guess.
Always Wordsworth.
Tom Hardy.
No, also a good guess, actually.
Byron.
No. You think? Give up. Philip Larkin.
I am so annoyed. I was gonna say Larkin, and I felt completely inhibited. Damn.
There you go. So yes.
And now for the poetry of the other Larkin.
Precisely. Very good. Yeah, I like that poem because it's so unlike the popular image of Larkin the miserable devil. Anyway, there you go. Right, let's draw a few more and introduce a bit more of the notation that's used for describing these. So let's look at M equals 1. So if I draw my Fermi surface, let's start with the cosine harmonic. So the cosine harmonic is +1 at phi equals 0. It is 0 at phi equals pi over 2. It is -1 at phi equals pi, but this is just the modulus, so we always draw things outside the Fermi surface, whether they're negative or positive. And it's 0 again here. So you can sort of join these things up. And now our sign labeling is important because this half is positive and this half is negative. So there is a change in phase of the superconducting order parameter as we work around the Fermi surface, and a new feature has appeared, which is that we have a node in the order parameter that is a point where delta is 0. Makes sense, right? The only way we can get from positive to negative. So this obviously breaks rotational symmetry, but it has a mirror symmetry about the line joining the nodes, or well, it's anti-symmetric about the line joining the nodes if you include the phase. And let me not mention the labeling. Let's look at the sign harmonic first, and then we'll see why we need a good labeling convention for this. So clearly the sine harmonic is just a rotated version of this, right? The sine is 0 here and here. Its positive lobe is here. Its negative lobe is here. And it has its mirror there. So both of these are P wave, because they're both m equals 1, but they're distinct from each other. And so we should have a label that describes which one we're talking about. And what people normally do is to label these as P alpha, where alpha is a function of x and y that is 0 where the nodes are. So it's a particular way of indicating where the nodes fall. So that labeling convention would tell us that this is Px because the nodes lie where x equals 0. And this is Py because the nodes lie where y equals 0. Okay. And we can make, obviously, the complex harmonics by cos plus I sine. That's just a mathematical identity. And so that state is labeled Px plus Ipy, or since there are only two that you could be using, often people just call it P plus Ip. It is hard to draw a picture of P plus Ip because the modulus of f, if it's going like e to the I phi, is also 1 everywhere around the Fermi surface. So the picture for P plus Ip looks very like the picture for S wave. And there's no great way with chalk to indicate that the phase is continuously winding as you go around the Fermi surface, but that's what it's doing. So this pictorial scheme is good for real harmonics. It's not so good for the complex ones.
But it's where a color-toned PowerPoint comes into.
Precisely. So if you've got something that can do a kind of color shading that rolls all the way around from red to red through the rainbow, then you can show that the phase is changing this way. But I'm not gonna, I guess we have colored chalks, but let's let's not even try.
You could draw arrows. Yeah, draw arrows.
Yeah, you could draw arrows. So yeah. Yeah, so this would be the gap. And in this version, those arrows are radial. Yeah, so that's not a bad picture of it.
And this has real physical consequences because for many purposes, Px plus Ipy will give the same thermodynamic responses as S.
Right, exactly. So if all you care about is the energy gap, and all you can measure is the energy gap, those two will look the same as each other. You'll have an exponential suppression of the specific heat capacity at low temperatures. Yeah, and you have to look quite carefully to see what the difference is. A curiosity is that, you know, we were discussing on Wednesday about how fully gapped states are generally preferred. So you might think that nature would tend to go for these gaps that don't have any nodes. And actually, a surprising number of materials do have nodes. And I'm not sure I really understand why that is. I would expect from general thermodynamic arguments that things like P plus Ip or D plus Id would be much more common than just one of the real harmonics, and they don't seem to be.
All you need to do is go to muon spin rotation and all your worries are over. In the sense that we've done a muon experiment that will tell you you have a time reversal breaking order parameter, everything's fine.
Indeed.
I was sarcastic for the people who are not experienced superconductivity practitioners.
Yes, this was a strontium ruthenate in joke, and it probably won't be the
But
last.
it's not, but it's not just a strong, I mean, the serious point is, they see this time reversal braking signature over a huge range of superconductors where there's no real reason at all to see it.
Mhm.
So you actually would falsely conclude that your argument here was correct.
Mhm.
If all you had was mu stuff.
So what are they seeing?
Okay, that, I mean, that's getting technical, Stephen Blundell now has some ideas, I can talk to you about that afterwards, but I think it's too
Okay,
specialized.
not all stuff. Very good. Okay, so that's m equals 1. We've only got the two real harmonics. We distinguish them as px and py. Let me just do m equals 2 because it's a case that comes up a lot in nature. Yeah, so
So I guess for an isotropic system, there's no physical distinction between px and py.
that's right, and I could make real superpositions where the nodes just moved. Yeah, exactly. So
Are there cases where this is important? Maybe if it's only in that case.
So one case will be under strain. If you started off with a cubic material or a square material that had these superconducting states, you'd expect px and py to be degenerate in the fourfold rotationally symmetric case, but then if you strained it and broke that down to C2, it should start preferring one over the other. By the way, that was what the strain experiments were sort of originally conceived to do. If you thought that strontium ruthenate was a p-wave superconductor, you should be able to lift the degeneracy between the px and py components by stretching or compressing. And so you should have seen the superconducting transition split into two, one where it went into px or whatever the favored one was, and then at a slightly lower temperature, one where it went into p plus ip. So of course that wasn't seen. We think we now know why. Am I right in remembering it was Jim Sauls who
Correct,
proposed that experiment? It was at one of the advanced working groups in Royal Holloway.
yeah, it was,
Mhm.
yeah,
Very good. Fruitful suggestion.
yeah.
Good.
Showing that one of the rare occasions where advanced working groups achieved something.
Yes. Well, I got a ride in Claudia's Lotus, so that was although, including the time it took me to get into and out of it, it would have been quicker for me to walk. Right, any other questions on m equals 1? If we draw something with more nodes. Good. We're not going to go beyond m equals 2 because we can see how this works, but m equals 2 pops up in so many materials that it seems worth saying something about it. So m equals 2 cosine is +1 here, it's got a node here, it's -1 here, it's got a node here, +1 here, it's got a node here, -1 here, got a node here. So something like this, plus, minus, plus, minus. And the nodes lie on these lines. This is a little bit more interesting when you think about what to do with the letters. So this is the line y equals x, which is the line x minus y equals 0. This is the line y equals minus x, which is the line x plus y equals 0. So I want a function which is 0 on either of these lines. How do I make one? Multiply them together. Multiply the two things that are 0. So this is d x squared minus y squared. And that function is chosen because it is 0 precisely along those two nodal lines. And then the sine harmonic now has its nodes at the principal positions plus, minus, plus, minus. And this is easier because clearly this is the line 1 equals 0. This is the line x equals 0. So the nodes now are where xy vanishes. Okay. So in 2 dimensions, those are our only options. The number of harmonics does not increase as m increases. We just get 2 at every value of m. And so you could easily write f wave and g wave and so on examples. And all of the real harmonics except m equals 0 have nodes, and the number of nodes increases by 2 every time you go up. Good. We will talk shortly about physical consequences of having the nodes. There are lots of physical consequences of having the nodes in the gap. But I want to say something first about how this looks for 3-dimensional order parameters. Any questions on 2D?
Like, well, a comment. I presume at some point we then go on to, so you're thinking of the orbital part of the wave function here.
I will discuss it in this lecture, even what we're doing with the spins.
And how that gets
Yeah.
usefully tedious. Absolutely, yeah, absolutely.
Yeah, that will fit in before the end. So we'll say something about that after we've done the spatial ones.
Is there a reason why the higher TC compounds would be not tested? Let me make this ask that question a bit better. It basically non-S wave ones are using 2 examples that have more and more nodes. So if you look at the delta, which is sum on all k delta k, might make it smaller.
Yeah, no, I agree. So generally speaking, if you don't see S wave, it's because there's something preventing it. The simplest example for the high TCs is that it's forming superconductivity out of a repulsive interaction. And you can't form S wave superconductivity out of a repulsive interaction, but you can form some of these other channels out of a repulsive interaction because you can effectively flip the sign of the pairing interaction by flipping the phase of the superconducting order parameter. So something which has a plus load talking to a minus load can pair even if the interaction is repulsive. We will look at that more carefully when we do the sort of where do these things come from. There's a generalized version of the gap equation where the interaction depends on K. And one can show that for the right K-dependent interactions, which includes some repulsive cases, it's actually optimal to pick D length.
But the highest TC superconductors we know are the hydrides. And to the best of our knowledge, the hydrides are S wave.
Yeah. Yeah, I mean, I think it's absolute size of TC has a lot to do with what the nature of the normal state is and how you're engineering the pairing.
Yeah.
I mean, there was this sort of back of the envelope argument for a long time that TC would never get above about 30 Kelvin. And that had to do with, typical Debye temperatures and what fraction of the Debye temperature you could reasonably get to. But of course, that assumed that the pairing was always going to be virtual phone exchange. And bandwidths for magnons can be much higher than bandwidths for phonons. And so in principle, these unconventional pairing mechanisms can go higher. I remember going to a conference in Trieste once where Piers Coleman said we should have a session where we identify the big questions in the field. And 2 of the 10 questions that the audience selected were, why is TC so high? And why is TC so low? Yeah, both of which were good questions. Okay, anything else before 3? Yeah.
So you argued why you expect D wave instead of S wave. But couldn't you make a combination that doesn't have these nodes, just like you did for 3A?
Right, exactly. So you could easily make a combination that doesn't have the nodes. So e to the 2i phi can obviously be made as cos 2 phi plus I sine 2 phi. That would look like, here's fun. So again, it's constant modulus. And now that's why I do twice as we go round. Yeah, this is d plus id. So yeah, for any of these, I can make a fully gapped example. And as previously discussed, it's not completely clear to me why this doesn't happen more often.
But I think the right thing to look at if you have, say, a crystal field, I mean, you have a square lattice or something like that, is actually degenerate.
No, I mean, if you don't have isotropy, then you shouldn't be expanding in this basis in the first place. So you should be, the reason for using these things is that they're irreducible representations of the complete rotation group. If you don't have the complete rotation group, you shouldn't be using these functions. You should then be using irreducible representations of the point group of the crystal. So that's just functions, for example, if it's fourfold rotation symmetric, those irreps are plus, 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 minus, 1i, minus 1, minus I, and so on.
And I think they're not degenerate, right?
No, right, and yeah, okay, that's
In most materials, that's what you have to do.
But they're not degenerate in 2 dimensions,
Yeah.
right? But you can find a symmetry protected degenerate combination of in 3D d yz plus I dxz
Mhm.
in a tetragonal material.
Thanks.
Yeah, and this is to do with higher dimensional irreducible representations in the Greek theory language. Yeah, so I mean, all of these points are good. As previously emphasized, when we start thinking about the lattice, we should, properly speaking, completely change our language because we've changed the symmetry group. People actually continue to use terms like S-wave, D-wave in the lattice case, but only really to give you an idea of whether there are nodes and where they are. Any more on D equals 2? Excellent. I have not thought about what I'm going to do here.
I wish I was in characters only for nights in Valley Grand. I would swim over the deepest ocean only for nights in Valley Grand. But the sea is wide and I can't cross over, neither have I wings to fly. If I could find me a handsome boatman to ferry me over to my love and die.
We've got into songs now. This is bad news. Will be a show tune by next week. Okay.
Danny boy.
Okay, so D equals 3 is similar in spirit, but the harmonics are more complicated. So in the D equals 3 case, we know how to do this because we've got these 2 angles. So we can just use the usual polar coordinate scheme with theta and phi to parameterize our unit vector. This now points to a point on the sphere, and a function of such a unit vector can be expanded as a double sum, n equals 0 to infinity, m equals minus L to L of sum and now these YLMs are just the usual spherical harmonics. And the spherical harmonics are defined with complex dependence on the azimuthal angle. The dependence on the polar angle is always real. So as we did in 1D, we're going to take combinations of them, sorry, as we did in 2D, we're going to take combinations of them in order to make real functions that also have nodes. So the real harmonics are made by just taking the sum or difference of the two oppositely circulating harmonics with the same modulus of m. And so, as an example, we might look at L equals 2. So there's y20, which is just the associated Legendre polynomial. That looks like 3 cos squared theta minus 1. And that cos theta has the same angular dependence as z. So cos squared theta looks like z squared. This is isotropic. So people write it as r squared, right? Because it has no angular dependence at all. And so this function is called d3z squared minus r squared, because it vanishes when 3z squared minus r squared vanishes. And if we draw it, this is harder to do, but let's try. So it's got a nodal line around the sphere at this height, 53 degrees or thereabouts. And it's got a partner, obviously, in the southern hemisphere. And so you can imagine drawing on top of these nodal lines some sort of bulgy bit here. And you have to imagine rotating this all the way around the sphere. And this is plus, and the lobe at the side is minus. And I'm not labeling the other one because that goes all the way around, so it must be the same.
So for what reason did you draw the white ellipses there?
Oh, that's just to show that it's a 3D sphere. Yeah, exactly. So yeah, they've got nothing to do with the superconducting order parameter. I'm just trying to show it's a sphere, not a circle. Okay, so that's one of them. And then we have y 21 plus y2 minus 1. So that goes like sine theta. That turns out to be the associated Legendre polynomial for this value of mod m. And it's the sum of the two complex exponentials. So it goes like cos phi. Have I got that right?
The Legendre polynomial depends only on the element.
The associated Legendre polynomial depends on L and mod n. So it changes according to mod n. So you get the second one. Yeah, yeah. Sorry, I think I've. This actually looks like this. Yeah. We'll have to check that, but I think that's what you get. One can look these things up.
It has to be that because it's always going to be 2 theta, but you're taking a single gradient, so you can't change 2 thetas to thetas.
Okay.
The sine theta.
Yeah, very good. Okay, great. So that is the answer. So if I draw this, well, what I can do is to note where its zeros are. So these two factors taken together look like x. This factor looks like z. So this thing vanishes where the product of x and z vanishes. And so this is dxz. And you can sort of draw it by noting that it's 0 when x equals 0 and it's 0 when z equals 0. So if I draw my sphere again. Really was 3D. So x equals 0 is this plane here. Z equals 0 is the equatorial plane. And so it's a function which vanishes whenever it hits either of those planes. And so you can see that it's going to have 4 lobes, one kind of sticking out over here. One sort of over here, one here, and one here. But now those lobes kind of wrap round and vanish when they hit this plane. It gets kind of hard to draw, but it's this quadrant of the sphere is occupied by a positive lobe, this quadrant negative, this quadrant positive, this quadrant negative. No, it isn't. It's actually different, and that's because of the sort of geometry associated with closing up towards the pole. Yeah, no, so they're not just rotated versions of each other. But obviously this one, y21 minus y2 minus 1, is just a rotated version of this because it has the same theta dependence, but now sine phi. And so now this combination looks like y, and this is z. So this is now dyz, and that is just a rotated version where this plane is pulled round to here. Right? So I won't draw it, it's just rotated around the z-axis by 90 degrees. And then we've got 2 others, y22 plus y2 minus 2. So this has a trivial theta dependence. Not quite trivial, but just signs. So that goes like sine squared theta, and then obviously it's cos 2 phi. That doesn't look perfectly like any of my coordinates, but I can make it do so by noting that cos of 2 phi is cos squared phi minus sine squared phi. And now this first bit looks like x squared. This bit looks like y squared. And we've actually discovered that one of the harmonics in 3D looks like one of our 2D harmonics. So the maximal mod m ones always kind of look like the cylindrical ones because they have all their variation in the azimuthal direction. So we get a dx squared minus y squared here, which if we draw it, has its nodes at x equals y and x equals minus y. So those make planes that cut through the sphere along these kind of cross-shaped nodal lines. And so it's just like taking an orange and cutting it into 4 equal segments. So all of the non-trivial angular dependence is going on here. So this quadrant contains a plus lobe like that. That reaches a certain distance round and then turns into a minus lobe, and then a plus lobe, and then a minus lobe.
Are you saying the projection of that in XY plane is the 2D version?
Exactly. Yeah. Yeah, and there's no these maximal mod m ones don't really have significant dependence on the polar angle. They're just like natural 3D extensions of the 2D ones. And just for completeness, we have y22 minus y2 minus 2. So that's sine squared theta times sine of 2 phi. again, I can write this as sine phi cos phi, and now two of those together look like x, two look like y, and so we get dxy. And just as in 2 dimensions, that's just a 45-degree rotation of this one around the vertical axis.
Also, it's also the same of that one rotated the other way.
Yeah. Yeah, that's right. Yeah, so it's yeah, which ones of these you consider to be a group kind of depends on the environment you're operating in. So there are crystal field questions there. You could consider dxz, dyz, and dxy to be a natural trio, which would be appropriate if you were in a sort of octahedral environment. Or you could consider dxy and dx squared minus y squared to be a natural pair, which would be appropriate if you were in a more cylindrical environment. Good. Okay. So that said something about just the classification, really, of these non-S-wave order parameters. Hopefully now you could in principle take generate the complete set of possible D-wave orders, F-wave orders, G-wave orders if you wanted to. I don't think there is a convincing case in nature of order parameter symmetries above D-wave, but feel free to correct me if you know of one. But they're quite easy to get in theoretical models, particularly with triangular lattices and things that have a natural six-fold rotation. Okay, so let's finish today just by talking about some consequences, which we'll unpack as we go into next week's lectures. So consequences of unconventional, an overused word, I really just mean non-S-wave order parameter symmetries. And perhaps the most easily observable one is the way you have nodes in the gap. If you do, those nodes host nodal quasiparticles, so-called because they are quasiparticles that live at the nodes of the gap. In the original S-wave BCS state, you basically had a vanishing density of quasiparticles at low temperatures because you had to pay an energy mod delta to create them, and mod delta is finite everywhere. But now, in all of these other cases, at least with the real harmonics, we have line nodes on the Fermi surface, where line nodes in 3D, point nodes in 2D, where the order parameter goes to 0. And if the order parameter goes to 0, the dispersion relation goes back to being the dispersion relation of the metal. And so you have gapless excitations at those points. It's interesting to think about their dispersion. So if I draw this case, for example, in 2D, let's think about the D-wave order parameter where the nodes are here, and let's focus on this one. I can think about the dispersion relation near this point, and of course there's a difference if I go in Kx or Ky. So going in the Kx direction, let's draw this with the origin chosen to be the nodal point. So going in the Kx direction, I have an approximately linear dispersion whose slope is set by the Fermi velocity of the underlying metal. Right? That's just the same dispersion that you have without pairing because you don't have any pairing. But if I go in the Ky direction, a gap opens, but it opens because the superconducting order parameter is becoming non-zero. And so that, that's coming out of the board towards you. That's going into the board. So in that direction, it's much flatter. Because what's causing the energy to rise there is just that you're following the gap as it grows. Right? And the gap, the bandwidth of the metal is electron volts, maybe. The gap is a few milli-electron volts. And so the nodal quasiparticles have this sort of cone-like dispersion, but it's a very anisotropic cone. And there are interesting physical consequences associated with that, which is, for example, if you excite nodal quasiparticles, they spread round the Fermi surface much more than they spread away from it. So if I make if I put a few nodal quasiparticles in somehow, they make a little banana-shaped Fermi surface, because if I imagine filling this anisotropic cone with liquid, the liquid would go much further in the flat directions than it would in the steep ones. So that's one consequence of having the nodal quasiparticles. What does that cause? It restores a power law in the low temperature specific heat. So the conventional BCS state has a full gap, so the specific heat is exponentially suppressed at low temperatures. Having nodal quasiparticles restores a power law because you actually do have excitable degrees of freedom all the way down to 0 temperature. Now it's just there are fewer and fewer of them as you work down towards the node.
This is really a question, but I think I know the answer. I should be thinking of those as W-U quasiparticles.
It doesn't matter really, because when delta equals 0, the Bogoliubov quasiparticles go back to being the conventional electrons and particles.
But if they've got this skewed dispersion.
Yeah, if you go to a finite density of these, and which forces you to go away from the strictly nodal location, then yes, they're Bogoliubov quasiparticles. That's right. But thermodynamically, all it sees is the density of states, and so it's the density of states associated with that gapless, distorted conical dispersion. Yeah.
White electrons and holes, right? Because they still can't carry a charge. They're deep in a superconductor, you create that. You can't define an electric field around it. It's like, there's a subtlety with
that's correct. So you're still in a superconducting environment with everything that implies about electromagnetism not being normal. But in terms of entropy, which is what you're measuring with the specific heat capacity, they look as if they were just regular electrons with that dispersion.
Actually, but you could that would really give long conclusions about their ability to transport things.
Yeah, no, very good point. So yeah, you always do have to remember that you're in a superconductor. These are Bogoliubov quasiparticles. Yeah, but it's just that in the specific heat capacity that turns out not to matter. Yeah.
People talk about Bogoliubov Fermi. Is that something that only happens around the moon?
Yeah. So this is one such. Yeah, if I put in a finite density of these nodal quasiparticles, which I can do while remaining in the superconducting state, and I ask what the ground state is of that, then it's a Fermi surface like this, which just extends along the underlying Fermi surface direction.
So this requires a heat.
Requires?
No.
Yes, yeah, exactly.
So this is a comment, not a
Yes,
question.
go ahead.
When you look at spin fluctuation theories, it's perfectly possible to get what they call accidental nodes. So zeros in the order parameter that don't involve a sign change, right? And they would have the same power law consequences as these. So to my taste, the idea of complete destruction of the superconductivity by randomization is the cleanest or dirty, so to speak, cleanest way to identify an unconventional order parameter. Your thermodynamics of nodes What you're correctly talking about are the thermodynamic consequences of having these sign changing nodes. But they aren't unique.
That point's very well taken. So what we are doing here is saying, imagine that we had this, what would we see? It does not follow that if we see one of these consequences, we know that we have a D-wave order parameter. And lots of these probes can, lots of these features in experiment can be caused by other stuff.
Whereas total destruction of the superconductivity by non-magnetic scattering, there's no way around it. That really identifies an unconventional liquid.
Yeah, and we will talk about sensitivity to disorder, and there's a nice calculation in the Markey paper that I mentioned earlier of how that works.
Excellent.
Good. Let me make one other comment, because I promised we'd talk about spin. So far we've just been writing down the possible variations in K-space of delta, and we've been doing it for a BCS state in which the Cooper pair has been prepared in a singlet, right? So we had C dagger K up, C dagger minus K down. That's a singlet ordering, because if I move those operators through each other, I pick up a minus sign. So let me give an intuitive argument for what the relationship is between these things. Intuitively, VK is the momentum space wave function of the Cooper pair, which is made of the fermions at K and minus K. And you can see that because of where it appears in the BCS state. So we have an empty amplitude and so normally when we generate a multi-particle state, this thing that stands in front of the creation operators is the wave function. And that's basically true in this case with a few nips and tucks that we might come to later. So that's observation one. If we work in a gauge where UK is real, then the phase of VK is equal to, up to a sign change, depending on your definitions, the phase of this K-dependent order parameter. And so in particular, if delta is odd under inversion, then V will be odd under inversion. Sorry, I'm not doing a very good job of thinking things in a line here, but because we're almost out of time, I hope you'll forgive me. So yeah, item one, VK is the momentum space wave function. Item two, its phase behavior is the same as that of delta. Item three, if delta K is minus delta minus K, then by Fourier transformation, the real space wave function of the Cooper pair will also change sign when we interchange the particles. Again, you can sort of write out the Fourier transform to see that this is true, but basically inversion works the same in K-space as it does in real space. So if our order parameter is odd under inversion in K-space, our wave function is odd under inversion, which is particle exchange in real space. This is the spatial part of the wave function, however. The full wave function also has a spin part, which for singlet pairing is this, the usual singlet expression, and that's odd under exchange of the particles, i.e. it changes sign when you exchange the particles. The total wave function for two fermions has to be antisymmetric, because that's just the definition of fermions. And so if we already have a minus sign coming from the spin part, we cannot have a minus sign coming from the space. And so that tells us that we cannot use all of the order parameter symmetries we've been writing down for singlet superpairs. We can only use the even ones. So if I have a singlet superpair, I'm actually restricted by overall antisymmetry of the wave function to using S wave, D wave, G wave, and so on.
I've written L there, but you were using it. and
Yeah,
the
okay,
rest of the
so
time.
sorry. For 2D, yes, it would certainly be N. Yeah. So that's an important point. And presumably the reason why we see so many more D-wave superconductors in nature than P-wave superconductors is that it's easier to make singlet Cooper pairs than it is to make triplet Cooper pairs. Obviously, if I allow myself to make Cooper pairs where the spins are parallel, then that's then even under interchange of the particles in the spin part of the wave function. So then I have to use the odd real space harmonics, and that will be P wave, F wave, and so on. So there's a symmetry restriction, at least in this simple case where spin and spin and space are the only two things we have to think about, which says that you have to have one of them odd and the other one even. Good. Now, of course, there's always a question then about what's causing what, right? So if you see a P-wave superconductor in nature, you could say, well, it wanted to be P-wave because of details of the pairing interaction, and so it was forced to be spin triplet by the symmetry argument. Or you could say it wanted to be spin triplet because of details of the pairing interaction, and so it was forced to be P-wave by the symmetry argument. And this discussion doesn't answer the question of which of those is the case, and it could be different things for different cases, but it just restricts the possible combinations of spin arrangement and real space order parameter arrangement that you can have. There are footnotes to that about odd frequency pairing and orbitals and this Blavatsky stuff, which we may come back to, but for now, let's leave it as a clean statement that for singlet pairing, it's S wave, D wave, etc. For triplet pairing, it's P wave, F wave, etc. Good. Any questions on this sort of introduction to anisotropic pairing? No? Yeah, please.
Would you use sort of transition between different order parameters and say D wave to S wave, T wave besides using string, for example?
I mean, certainly in principle, yes. The question of what you would change to cause it to tip over from one order parameter to another, I don't know a sort of easy answer to. In particular, if your pairing interaction was non-retarded, you'd be more likely to get transitions between different symmetries of D wave than you would between D and S. Because roughly speaking, S tends to be thermodynamically preferable unless it's forbidden. And so in materials that can do S wave because of the nature of their Hamiltonians, I would imagine it's quite hard to get them to do anything else. Whereas in ones that can't do S wave, you have lots more options, but it's more likely, I would think, that you transition between those options than between D and S.
I mean, there are plenty of papers you can find in the literature with toy models. I agree completely with what Chris was saying there, with toy models for going between D and P, for instance, as a function of the parameters of those toy models. So, you know, if that's the kind of thing that you like, then those are findable, and I could email me, I could send you some examples.
I think also with the disorder, you can go from D to S, but it's sort of delicate, because if you have very weak disorder, you'll still have a mean field D wave solution. But there's a regime, if you think about that, where if you have enough, as Andy pointed out, disorder will kill the D wave at a mean field level. You'll have a cost of rock argument. But then what will happen is that you'll have, puddles, if realistic disorder, you'll have puddles of D wave. in small regions, so they can sort of communicate and you'll find diagram is globally S-wave.
Mhm.
So that's, weird, very strange, but it really is intrinsically sort of.
Mhm. Okay, very good. Other questions or comments? Yeah.
So the P-wave case where you just said it's forced for the spins to be in a Hilbert state.
Mhm.
It is this square with, how do you square that with an expected magnetic response for triplets? So, I don't know if I'm asking this question right. The singlet makes sense to me because the spins drop out of the picture.
Yeah.
The superconductor doesn't like magnetic fields anyway. All is good. But how do you, is there anything with the P-wave case where the charge degrees of freedom are transmitting magnetic effects? The spin degrees of freedom have some system
Yeah, okay, I think I see let me try and paraphrase that question and see if it's still the same question. You're saying if the Cooper pairs are triplet, then they have magnetic moments. What am I doing putting something with magnetic moments in a state that's supposed to be showing a Meissner effect?
Is it okay because there's no magnetic fields anywhere, so you can tell?
I think that's basically the answer, but yeah, that's right. So, I mean, microscopically, I guess if you go sufficiently close to the electron, there's got to be a magnetic field caused by its moment. It's just that gets screened off quickly in the way that magnetic fields are screened in superconductors. So yeah, I think that probably is the answer. I haven't thought about it carefully. If I think about it and decide that's not the answer, I'll tell you in a later lecture.
But isn't it the case then that they wouldn't care about arbitrarily large magnetic fields? Because they would have the same spin susceptibility as the normal state.
From a Zeeman point of view, yes, but obviously there's still the orbital effect of the magnetic field.
That's true, but if it's a 2D superconductor, you put the field in the plane.
Right.
And then.
Yeah. So in that case, they shouldn't.
And, that has two aspects, right? One is this lack of Pauli limiting. So if you take the orbital physics out of the game and you apply a large field, then you Zeeman split the single Cooper pair. That's called the Pauli limit on the critical field. At the other limit, if you go down to small fields and study susceptibility, as Joe says, and you do your experiment correctly, if you've done your experiment correctly and you see a temperature independent Pauli susceptibility through TC, then you know you've got a particular kind of triplet.
Mm-hmm. But obviously don't use too much pulse power.
But don't use too much pulse power, don't mislead the entire field with research for 20 years, that's good. I mean, yeah.
Excellent. Other questions or comments?
I have a question related to what Sid was saying. So if you have a D-wave superconductor with large amount of disorder and it has become like this kind of puddles of S-wave, what would the specific heat look like?
A mess.
Very good. Yeah, so I've not thought about this problem, but it's probably messy. Good. Okay, we should probably start because that brought us to lunch. Thank you, everyone. Next lecture is Wednesday, and we will go a little further into how you actually get these unconventional parameter symmetries in models.